Okay, so I have finished about the fundamentals of chromatography, and now I will speak about the first family, the big family of chromatography, which is gas chromatography. And I will speak about the principle and the instrumentation first. After that, I will focus on the injector, the columns, and the detector. So now I will focus on the first family, big family of chromatography, which is the gas chromatography. The gas chromatography is a very important family of chromatography. And you know, of course, the second family is the liquid chromatography. There are a huge difference between gas chromatography and liquid chromatography. And of course, it differs on the nature of the mobile phase. Concerning the principle of gas chromatography, this is a separation method, of course, for the gas compound or the compound likely to be vaporized without decomposition. Here you have the representation of the system with the stationary phases, the mobile phase, and two different compounds. Then, the principle is based on exchange of gas molecules. Be careful, this is only gas molecules. There is no separation of liquid molecules in gas chromatography. So this is based on exchange of gas molecules with the stationary phase. Then we see the interaction between the molecules and the stationary phases. And the stationary phases, the nature of the stationary phases is liquid or, sorry, this is not off, or solid in gas chromatography. So the stationary phases is liquid or solid. And the mobile phase is a gas. It is impossible to have a liquid in gas chromatography for the mobile phase. So, of course, this is a gas. So if it is a gas, you need to have a nature. And the nature of the gas in gas chromatography, which is the mobile phase, is the fact that this is an inert gas. For example, you can have the helium, the nitrogen, the argon, the hydrogen. So the carrier gas is inert. And it is inert. This is a major properties because it needs to be inert to analytes and stationary phases. There is no interaction between, no chemical interaction between the carrier gas and the analytes or the stationary phases. The carrier gas is only here to push the sample in the stationary phases, on the stationary phases. So you have to choose the carrier gas, of course, and to choose the carrier gas, you can see first the nature of the detector, because some carrier gas are not compatible with some detectors. So of course you have to see that, and also you can see the running cost, because this is important to see, of course, always the cost. But the most important thing on this slide, and for gas chromatography, is the fact that there is no interaction between the carrier gas and the stationary phase, and no interaction between the carrier gas and analytes. Be careful, because this is one of the most important things in the gas chromatography. So when we speak about the carrier gas, we speak about the purity of the carrier gas, of course. As I told you previously, we need to avoid any interaction between the carrier gas and the analyte or the stationary phases. Then, of course, you need to be sure that there is no impurity in your carrier gas, which can cause any damage with the interaction with stationary phases or analytes. So it is imperative to verify, to control the high purity of the gas. And for that, we have some reference gas the reference is like this. For example, the A.0 or the Na0. A indicates the number of 9 present in the purity number. So for example, we have a 6.0 or N16. For that, the purity is 99.9999%. There is 9 in this number. If I have a 3.5 or N35, the purity is 99.95. You have 39 and 15. That's very simple. And in GC, we usually use a purity of 5.0 or N15 purity. Then this is important to control this purity, and we cannot work with a 3.5 gas, because in that case, for example, we can have some impurity which cause damage in the separation with interaction with the analyte, for example. The nature of the gas, the carrier gas, is also important in terms of optimization, because there is no interaction, but you can have some influence on the linear velocity of the mobile phase, the flow rate. And you see, for example, in this particular example, the representation of the von Dimter equation for different gas, the nitrogen, the helium, or the hydrogen. And you see, for example, that with the nitrogen, in that condition, in this condition, you can see that we cannot work with the same flow rate, the same linear velocity of mobile phase, because you don't have any mass transfer phenomena with the hydrogen as compared to the nitrogen, where you see you have an increase of the HAPT, which is the height of theoretical plate, and then, of course, a decrease of efficiency and a decrease of the resolution. So we can work with 40 centimeters per second with the hydrogen, and only around 15 centimeters per second for the nitrogen. And then, of course, in terms of optimization, it is much better to work with the hydrogen in that case. The second parameter, which is very important in gas chromatography, is the temperature of the oven. The temperature is the major parameter in GC. There is two major parameters in GC, the temperature and the nature of the stationary phase. We will speak about the nature of the stationary phase later, but concerning the temperature, of course, we know that the retention time varies according to this equation. So log of TR, of the retention time, is equal to a factor A, over the temperature plus B. It means that if T increase, if I increase the value of T, of course, the retention time decrease. And we see that, of course, this is a parameter, a very important parameter to optimize the separation, especially to optimize the analysis time of the separation. So if T increase, if the temperature increase, the retention time decrease. So here is an example about the effect of the temperature on the separation. And this is the representation of the equation for a series of 4 homologous compounds. So you see, we consider these 4 homologous compounds, and these compounds are quite similar, and then have the same behavior in terms of separation when I increase or decrease the temperature of the oven. So here you have the log of TR. So here, this represents the retention time, and if I go in this direction, of course, the retention time increase. And here I represent the 1 over the temperature. to on this direction, if I decrease the temperature, of course, 1/T increase. So you can see that if I decrease the temperature, the retention time increase. And then, of course, the higher the temperature, the faster the separation. That's very important. So if I go on this direction, so I decrease, I increase the temperature, of course, I decrease the retention time. At very high temperature, there is no more separation. So in that case, you see, this is impossible to have a difference in the retention time, and then this is impossible to separate the compound. Another example, in that case, on a series of heterogeneous compounds. So here you consider 3 different compounds with 3 different behavior. This is the same representation. So if I go in this direction, I increase the retention time. And if I go in this direction, I decrease the temperature. Three different temperature, 3 different possible temperature, the T1, the T2, and the T3. And if I have to choose the better separation, of course, I have to choose the T2, because in the T1, I see that here I have a cross between the compound 1 and the compound 3. Then I have no separation of these 2 compounds. There are a co-elution, and I have the separation with the compound 2. For the T2, I have the separation of the compound 3, compound 2, and compound 1 and compound 2, I'm sorry. And for the T3, I have the separation of the compound 3 and the coelution of the compound 1 and compound 2. Then at T1, the compound 1 and 3 are not separated. At T3, the compound 1 and 2 are not separated. And at T2, all compounds are separated. It is also possible to separate, to increase, to optimize the condition. If, for example, I regard this temperature here, for example, in T0, and in that case, the retention time of all the compounds, which are separate, are better as compared to the T2. So I can also work in T0 to optimize the separation. And then, of course, if I decrease the temperature, I increase the temperature, I'm sorry, I decrease the retention time.